So the final speaker of this session is Xiaoyi Liu. Xiaoyi received his PhD from the Institute of Computing Technology at the Chinese Academy of Sciences in Beijing. And since 2012, he's been a postdoc at the Ohio State University.
Okay, thanks.
Thank you.
Hello, everyone. I'm Xiaoyi Liu. I come from the Ohio State University. Now I'm the postdoc in Dr. Panda's group. Today, I want to present this paper. It is talking about the designing optimized MPI broadcast and Allreduce for mic InfiniBand clusters. Okay. This is the outline. Firstly, I want to give some introduction, and then I will discuss the motivation and also the problems addressed in this paper. And then I will present some design issues in the paper and also give some evaluation and then conclude this presentation. Okay, now actually the HPC applications scale beyond 400,000 cores. For example, for TAG STEMB supercomputer systems, and also the MPI has been the standard programming model for the parallel applications. And the MPI actually defines the collective operations to implement the group communication operations. And also the parallel applications commonly rely on the collective operations owing to their easy programming and also the performance compatibility. So it is critical to design the collective operations to improve the performance and the scalability of the HPC applications now. So nowadays, the multi-core processors are everywhere, right? For example, your laptop, desktop, server machines. Okay, and also the InfiniBand is very popular in current HPC clusters. The accelerators and the co-processors like the mic becomes commonly in the high-end systems. And also the emerging HPC hardware lead more and more heterogeneity in the current systems. So it is necessary to optimize MPI communication libraries for such kind of emerging systems. So one of the most important features of a mic is that it's x86 compatible. So it means we can reuse the strong Xeon software ecosystem. For example, we can reuse the programming model libraries and tools, something like that. Okay, so Xeon Phi is the first product line based on mic. It already used in top 500 systems like the Tenhe 2, which is the fastest supercomputer in the world, and also STEMB talk. So in mic clusters, we have more flexibility to the MPI applications. For example, like here we list 4 different models for the MPI applications. For example, the host-only model, which means the MPI process actually running only in the host. And also there's offload model. It means we can, the MPI process actually running in the host, but we can offload the computation intensive part to the mic. Okay, and the third one is the symmetric model. It means we can launch MPI applications in the host and also for the mic. Then they can communicate and also work together. So the last one is co-processor only. It means we just launch the MPI applications on the mic itself. Okay, so MPI is developed by our group, and is a high-performance open-source MPI library for InfiniBand, also other RDMA-capable networks. So currently, it has been used by more than 2,055 organizations such as HPC centers, and industry, and also university across 70 countries. So for more details, you can go to this web link. Okay. After introduce the background, we want to discuss some motivation and the problem addressed in this paper. Okay, so mic architectures are leading to heterogeneous systems. So mic coprocessors actually have slower clock rates and also very limited physical memory space. So the heterogeneous mic clusters also introduce many new communication passes. with different performance trade-offs. So we can see that it's critical to design the communication libraries like the MPI to carefully optimize the communication primitives on such kind of heterogeneous systems. So here, this slides, we will discuss about the communication data movement on the mic clusters. For example, here we can see this is the typical intra-circuit communication. This is the inter-circuit communication. This is the inter-node host-to-host communication. And then this is intra-mic, the MPI process communicated in the same mic. And then this is the inter-node mic-to-mic communication. And also this is the inter-node mic-to-host communication. We can list more passes. So the basic thing is that we want to say we need to optimize this data movement to hide such kind of complexity. So the other important thing is the peak bandwidth we have observed for the communication passes. For example, this is the host IB host communication pass. The peak performance is more than 6,000 megabytes per second. Okay, this is the host mic communication is near 7,000 megabytes per second. Okay, this is read data from IB device to the mic memory. These are more than 5,000 megabytes per second. But here we see if we read the data from mic memory through IB device, then it only less than 1,000 megabytes per second. So this is the big bottleneck. So we need to avoid communication passes involving IBHCA reading data from mic memory. Okay, this is the bottlenecks in the system. But if we take a look at the MPI collective design, for example, this is the basic recursive doubling design for the Allreduce. So the step one is the intra-host in the intra-mic reduction. And then we will do the intra-node host-mic communication. And then the third step is the inter-node mic-to-mic communication. Actually, the mic-to-mic communication is very slow, as discussed in the previous slides. Okay, so finally, we'll do the intra-node and intra-mic broadcast. This is the default design right now. Okay, so if we suppose there's n nodes and the 2 leaders per node, it means 1 leader for host, 1 leader to mic, there will be log to n inter-node steps, and all of these steps will involve IBHCA reading data from mic memory. Actually, this will involve lots of the communication overheads. Okay, so if we take a look at Bcast, for example, the basic kilometry-based algorithm, similar things. The first step is the inter-host mic-host communication. Okay, the second one is the inter-mic communication. In this step, the communication speed is very slow. Okay, the third, lastly, there will be a host-mic communication for the intra-node and in the intra-mic broadcast. So here, if we suppose the root of the MPI Bcast is a mic process, then the step one will involve several send operations, and also these send steps will require HCA reading from mic memory. So this is very slow, and also all subsequent transactions that involve a co-root on the mic will experience similar bottlenecks. So the overheads will also propagate to host level transfers. All of this will involve high communication overheads. So in this paper, we want to address these questions. Firstly, can we design a generic framework to optimize such kind of collective operations on the emerging heterogeneous systems? Secondly, how can we improve the performance of common collectives like MPI Bcast, MPI Allreduce, or MPI Allreduce on mic clusters? Thirdly, we want to answer what are the challenges in improving the performance of the intra-mic phases of collective operations. Okay, finally, the mic is a highly threaded environment. Can we utilize OpenMP threads to accelerate? Okay, now we want to show our design for the optimized collectives for mic clusters. Firstly, I want to discuss the MPI, our design objectives. So, firstly, we want to minimize the involvement of the mic cores while progressing collectives. Secondly, we also want to eliminate the utilization of high overhead communication paths, just as we shown. So thirdly, we want to improve the performance of inter-mic phases of collectives. So our basic idea is we want to split the heterogeneous communicator into two subgroups. And the two subgroups are like the host communicator that's only comprising of host processors and processes, and the second one is the mic leader communicator. It only includes the mic leader process. So this picture shows the host communicator. It only it doesn't include any mic processes. Okay, so based on this idea, we can see how to optimize the Bcast. Okay, the first step is still the inter-node host mic communication for the inter-host and mic broadcast. And then secondly, we will do the inter-node host-to-host communication. In this step, we can avoid the mic-to-mic communication. So certainly, we will do the host-mic communication for the inter-host and inter-mic broadcast. Okay, so we can see the inter-node communication done through the homogeneous host communicator. So the proposed design can completely eliminate the communication paths, for example, requiring the IBHCA reading data from mic memory. And also, we only require one hop over the PCI channel between each host leader and the corresponding mic leader. And also, we can offload the inter-node phases of the collective operation into the more powerful host processor. Okay, so, okay, now let's discuss MPI Reduce and MPI Allreduce design. This is a little bit complicated. So we want to discuss different design schemes. So this first one is the basic design. Like in the first step, we still do the inter-host reduction and the inter-mic reduction. Then we will do the host-mic communication to exchange data. And then thirdly, the inter-node reduction between host to host. This is the horizontal and then vertical. Okay, so the last step is the inter-host and the inter-mic broadcast. So we can see the inter-node communication still goes through the host communicator. So if we can see the basic design scheme, we can eliminate the IBHCA reading from mic memory. And also each mic leader performs maximum of 2 transactions over the PCI, and also the critical communication steps performed by host. This is the advantage of basic design. But however, there's also some overhead. For example, the first set of inter-mic Allreduce is still performed by the slower mic cores. Secondly, the inter-host phase cannot begin until the mic leader is done with inter-mic reduce. This means we cannot achieve better overlap. Okay, so we optimize this basic design. We can have a look at another design scheme. We call it direct. For example, here in the first step, we just do the inter-host reduction. This means each processor in the mic will directly send data to the leader of the host. And then in the second step, the inter-host reduction occurred. Okay, in the second step, there will be inter-host reduction. Okay, in the third step, there is a inter-host and the inter-mic broadcast. So we can see there's still similar benefit we can get, but however, the inter-mic computation will be offloaded to the host. So, but for this design, there's still some things. For example, the large number of transfers between mic processor and the host leader on each node, and also the heavier node on the host leader processor will be there. So for this discussion, we can see we can still further optimize. We call it peer-based design. For example, instead of do the reduction only occurred in the leader of the host, we can actually send the data to the corresponding process in the host for each process in the mic. So here like this, and then we will do the inter-host reduction, and then the similar inter-host reduction, and then the broadcast finally. Okay, so for this design, actually we can we have all of the advantages for the previous two designs, but we can also make the node more balanced for the host processes. So, however, there is a large number of transfers also there, but this cannot be avoided. Okay, so all of above the discussion is about the internal case. For internal cases, actually, we can also do some optimization. For example, this is the basic slab-based design. Okay, so here, for example, in this case, each slab for different communicator, the control information actually will write to control array 0, and the data will real data will be stored in the slab. Okay, actually the slab is the continuous memory space for the processes. So in this case, we can achieve better spatial locality for the data communication. But however, the control array used for updating control information and synchronization, but this array will be shared by all the processors in the communicator. So it will lead cache slashing. Okay, so we can give another design scheme to optimize the things. For example, the slot-based design. So here we want to show the column-based method. So okay, so the control information will be stored in the column 1 and the different rows, and then the real data also stay in different rows. So for this design, actually the slots, the process use different memory locations in the column to update control information and to synchronize the status. So this can reduce the cache slashing, but however, the data locations are also no longer continuous. So it means it will lack of the spatial data locality. So if we think about it a little bit further, then we propose the new design like this. We call it the staggered-based, staggered control array-based method. Here, actually, the control information will store in the slot-based design, but the real data will store in the slab-based design. So it means it is a hybrid solution. So we can still maintain the spatial locality for data, and we also can avoid the cache slashing. So these designs rely on the load leader to perform the reduction of via the shared memory, and also this may lead to load imbalance and the skewed execution for the leader. So we want to propose another optimization, like we can construct the tree-based designs for shared memory to balance the node. Also, the tree with configurable degrees can be used to customize for different architecture. And also, in the following slides, we also want to show some numbers with our. We use the OpenMP threads on the mic to further accelerate the compute operations. Okay, now I want to show some numbers with all of these designs. So our experiments conducted on the MPI cluster, we used up to 64 nodes, and each node we have 32 gigabyte memory. For mic, we only have 8 gigabyte memory. So each node will collected by Mellog's FDR switch. We use our MRPH2 and also the OSU microbenchmark to evaluate the results. In order to compare with other MPI library, we choose Intel MPI 4.1. Okay, so let's first see the performance number of MPI Bcast latency comparison. So in the left graph, we show there's a 32 nodes, and so there's a 2 MPI processor in host and 16 processor for mic. So we can see our proposed design can show 44% improvement. Okay, if we go to larger scale, like the right graph, there's a 64 nodes. We can see that our proposed design can outperform default MPI Bcast design by up to 72%. Here, we were unable to scale Intel MPI for up to 64 nodes, so we don't show the results in the right figure. So Next one is the internal MPI Bcast max latency comparison. Here we can see our proposed design outperformed default MPI Bcast mechanism by up to 48%. Okay, so for the internal MPI reduced latency comparison, we can see that our staggered control array-based design with 3 degree 2 outperforms default by up to 45% improvement. Okay, for the inter-mic MPI reduced latency comparison, similar things, we can see that this one shows the OpenMP benefits. So for the very large messages, the new design with 4 OpenMP threads outperforms default by up to 17%. For the internal cases, we can show up to, for example, 58% improvement. For the internal MPI Allreduce max latency comparison, we can show up to, for example, 52.6% improvement. Here, we also see similar things for inter-MPI. We can also scale to 64 nodes. Okay, with all of these designs, we also evaluate with the real application example. For example, here we choose the WindJammer for the performance comparison. This application heavily uses MPI Bcast. So here we can see that our solution can improve the performance by up to 16%. So here I want to give a conclusion. So in this paper, we proposed a generic framework to design collective in a hierarchical manner of emerging mic clusters. So we also explored different design schemes to improve inter-mic phases of collectivities such as MPI Reduce and MPI Allreduce. So our proposed design improved the performance of MPI Bcast by up to 72%, and also for MPI Allreduce up to 58% improvement. We can also improve the application execution time by up to 16%. So finally, in the future, we will extend such design for the performance of other commonly used collectives for emerging mic clusters. Okay, thanks.
Questions? Please go ahead.
Okay. Hi, this is a very good presentation. I had a quick question though. If you're assuming that the MIC card right now is a coprocessor, what happens when the MIC is integrated into the host?
Can you a little bit close to the mic?
Sure. In your presentation, you have shown the MIC card as a coprocessor card. What if the MIC functionality is integrated into the host? So it's actually not on the PCI link, but it's actually on the host side. Because you might have heard about the next generation Knights offering. It's actually has 2 modes in it. It can work as a coprocessor, or it can also be a host by itself.
Yeah, I think in this evaluation we use the symmetric model. I mean, the MPI processor will launch for both mic and host.
Right. So the question is, how much of your performance issue goes away just because you move the functionality into the host?
Okay. So, okay. Dr. Panda may can answer this question.
Yeah, so this is this presentation is based on the whatever is available currently in the market. Night landing is being still discussed. When it is available, we will reevaluate it again.
But do you have any, what do you expect the impact will be just because of that?
It's very hard. I mean, unless you see these technologies and how they are exactly integrated, what is the overhead, it is very hard to predict.
Thanks.
Okay.
Were you only using one mic on?
Yes.
Okay. Have you considered the multi-socket, multi-mic case?
Yeah. I think it is a future step. Good question.
Okay. One other question too. Have you compared the performance of your optimized ENVA pitch versus Intel's MPI implementation?
I think.
Compared to?
Compared to, yeah.
Yeah.
Compared to Intel MPI? Yeah. He showed the numbers.
Yeah.
Okay. Go back to those slides.
Yes,
I think we showed the numbers.
For example, we have showed this one. Okay, sorry. For example, this one. Actually, this is the Intel MPI, right? The green line.
Okay. Thank you.
Okay.
Any further questions? Okay, so if not, thank the speaker.
Okay, thanks.